start recording. I also didn't know that you could press them both at the same time. So thank you, ZM. This is very entertaining. See, but see, I also want to save the chat. Okay, I guess I'll just leave that to another time. ZMVPC3R5BM9V ZGXL. Oh my god, that's crazy name. That's perfect. All right. So yeah, I'm not sure if y'all have heard the explanation, but right now memory allocator today. Not an expert coder. I'm not sure like what I'm going to do. Although I do have to say, like I'm in college trying to learn more about systems programming. It's what interests me the most. So part of doing that is just throwing yourself into the void and see how to come out of that. And the way I found that how to do that was write a memory allocator from scratch. I'm going to be basing it off of Carnegie Mellon's malloc lab because I found it on Google. I found like the starting files. I'm not a student at CMU, so I just found it, right? But one of the first things, so let me see if I can somehow, let's see, can I open, I want to open, there you go, Nalloc. So name of my project, I've decided to name it Nalloc. There is not much of a reason to call it Nalloc. I just think it's a silly name. It's malloc, but the end just means either new allocator, not malloc, the pirate version of malloc, whichever one you want. And yeah, so oh wait, let's see. So stream stall pass broadcast. Yes, exactly. Like I've been looking at that, but it seems like I don't have that option. I'll have to look at it after I am maybe done with the stream because I do want it to. I don't want this to be like me trying to set up the streaming experience and all of that. But yeah, right now I have it on OBS. It's recording too, so I guess that's fair enough. But thank you so much. So yeah, I mean, as I was saying, all I have is sort of this will to get this done. As I said, this is the starting files for CMU's malloc lab. They also have the whole sort of infrastructure to measure the efficiency of your code, to measure, okay, how much memory you're using, how fast is it. So that's definitely something good because we want to focus on creating the sort of our own malloc rather than the infrastructure behind it. And yeah, so I've been watching some of the lectures, been trying to understand that, but this is all we have. So the plan is the following. I had like a little Excalibur here that I wanted to, like I was just playing with it before, and it's really not that much that I've done, right? Like I just wrote down sort of the policies you can have on memory allocation, and some of the data structures depending on what policy I choose. So worst fit is definitely one I would discard, or I guess like memory allocation policies is how do you decide or how do you manage your memory? No, it would be the way to explain it. And policies is precisely that. No, what is your decision with respect to that? First fit would be, you know how memory is sort of this layout. There are thousands of bytes, one next to another, and you can sort of think of it as this strip that's just really, really big. And first fit is where you go through the memory until you found a block of memory that's long enough to suffice the amount of bytes you need, and then you just provide it to the user. First circular fit, or next fit, is doing the exact same thing. It's just that whenever you start your search, you don't start your search from the beginning of the memory, but after the sort of after the last search ended. So if I am kind of like over here and I ask for, suppose that each of these little guys is like, I don't know, 1 byte or 4 byte, 1 byte. Then I'm going to go here and then I'm going to say, okay, suppose the user sort of asks me for, I don't know, 3 bytes. Then I'm going to go over here and then I'll say, okay, this thing, it's completely empty, right? And here I found a block of 3 that works. So I'm just going to allocate that and give it to the user. Now, when somebody calls malloc with a different parameter, say malloc 5, right? The search is going to start from here. Then I'm going to say, okay, is this block free? Well, no. There's 3 bytes occupied, and then then we go over here, and then you say, okay, this is free, so I'm going to give him these 5 bytes, and so on, and so on, and so on, and so on, right? Next fit is simply, rather than starting the search from here always, from this sort of initial position, we started from where the last search ended. So we're going to start here. And that sort of reduces external fragmentation of memory. Worst fit is the same as best fit, and but instead you sort of look for the biggest block of memory and then allocate stuff there. And best fit is just what it sounds like, right? What is the best one? What is the best block? The block that fits the amount that they're asking for the best. Oh wait, I haven't seen the chat. Oh my god, wait. So AI view streamer. Okay, buddy, you're getting banned. I don't know how to do that. Oh, there you go. Perfect. Let's see. Don't open that link. It's about. Oh yeah, for sure. So I mean, it's not necessarily a virus link, but better to be safe. Yes, agree. Do you plan on storing free allocated information in the buffer itself or in separate data structure? So I think what I'm thinking right now is, out of these policies, best fit seems to be the sort of the one I'm leaning more towards. Not only because it is a good policy, right? I mean, you cannot have a universal memory allocation policy, right? But best fit is definitely not a bad one. But it's also the fact that it seems to be a little bit trickier, right? First fit, you sort of have to go through your free blocks until you find one. Sure. But best fit involves sort of these other stuff on how to optimize the search for a good block. So in this case, and that's exactly what I've sort of written down here. I had it written down before because I had been thinking about this yesterday, and then today I said, like, dude, this is perfect to to like just start streaming, because I procrastinate a lot. So I it's difficult sometimes to find motivation to do stuff. So I decided to precisely start this Twitch channel, because I mean, my intention is not for people to become super famous or anything like that. It's just to like hold myself accountable, right? And have people that are like, oh, right, do you plan to do this? Like, how do we do this? Which is great. But best fit involves like all the data structures, like AVL trees, red black trees. And to answer your question, because I don't know, I'm going all over the place. I think that we would need to store the information inside the block that we provide to the user, right? It kind of depends on what information. Of course, if like the user, whenever they call free, they're going to provide you the pointer that you gave them. So in that sense, we need to know how big the memory block is, and that information we will store within the block itself. Because if we are to have a separate data structure, the searching time or the amount of time that it takes us to look in there is going to be a little bit more, when we could just have that information inside the block and know exactly its offset so that we can just access it directly. An example of it is if the user asks for something, then what we're going to give them back is going to be something like this, right? This sort of thing, where this stores a bunch of information from the user, right? Could be many bytes, But every single block of memory that we provide to the user is going to be accompanied by some sort of metadata, right? That information, it really depends on us. Like, we are the ones who decide what to put in there. I had been considering the following. So I think it's better if I just simply sort of erase all of this and like and like start from. Oh no. Okay, there you go. So let's see. Yes, per block metadata right next to the block. So if we have this, say, right, the user asks for some amount of bytes, n bytes, then what I'm planning on doing is we are going to get sort of this sort of separation of memory, where this huge block, it's going to be whatever we provide to the user. Sorry, I'm kind of slow when it comes to drawing. There you go. So this is going to be the user info, or like user data, right? This is all the data that the programmer we're providing this to, this is where they are going to store it. So the pointer in memory that we're going to provide to them, it's going to be this one. So we're going to give them the first byte of that huge user data block. Now, whenever they call free, we need to know how to free that memory, right? So in this case, I'm just going to say user data, then it's like n bytes, n bytes, n bytes. Okay, user data, n bytes. And the thing is, whenever we're given a pointer, we just know the pointer's value, right? We know something like, I don't know, 0xc E34. We don't know that this user allocated n bytes in the past. We don't have all that information. We don't know sort of whether there are blocks to the side that are also free, whether, right? We only know that pointer's value. So the strategy in this case, we need to free this information, these n bytes, would be right before the first byte of the user data, I'm going to include the size of this block, right? So in this case, that would be n bytes. And that way, whenever the user provides me a pointer and says, please free this, all I have to do is subtract 1 from that pointer. Oh, well, not 1, right? Like just go back by the offset of the size, which in the case of C++, that would probably be 4 bytes if we're talking about an integer, depending on the platform, of course. So in this case, something like C30, we go back 1 position, we simply subtract that from here, and then boom, now we know the size, right? Yes, exactly. So you just pointer out, sort of backwards, right? Yes, exactly. Even if that header is only a single field for now. So what we have is exactly that. We have the size. Now the question is size enough? Right? Do we need to include more metadata here? And I think that like this is something that's interesting to think about, because this would make for a very basic memory allocator. But another problem surfaces, and it's the fact that, of course, the user is not going to ask for only one thing. The user is not going to be like, oh, just give me 24 bytes for the entirety of my program. They're going to ask probably first, give me 24 bytes, and then later in the code, they're going to say, oh, give me 32 bytes now. Then later in the code, oh, give me 5, right? So in those situations, you're going to have multiple blocks sort of coexisting with each other. And what that creates is the problem of external fragmentation, where in your memory, you have these sort of batches that are occupied. I think it's better if I just use this bigger one, where the user has allocated, I don't know, these bytes here, and maybe these 2 over here, maybe these 3 over here, maybe all of these, right? Suppose now that the user frees this block of memory, and now they ask us, can you please allocate 4 bytes? And the problem with that is going to be that, do we have 4 bytes? Well, yes, right? I see 1 byte and then 3 bytes that are free. So that's 4 in total. But we cannot provide them the 4 bytes they want because we don't have any one single block that is 4 bytes long, sort of contiguously. And that's exactly what fragmentation refers to. No? Where as you free stuff from memory, your memory is going to have all of these little holes around. And although you may have enough space to suffice a request, that space is so scattered around that you cannot satisfy that request. So we don't want that to happen. We want to minimize that external fragmentation as much as possible. And another problem that surfaces is the following, right? So right now I'm saying, oh, this block is free, and its length is 3, sort of obeying the structure we have created up until this point. And then this block is free, and it has sort of a size of 1, right? Suppose that each of them is like 4 bytes, right? So I'm just storing like a tiny little number. The specifics don't really matter right now. And I suppose that I free this thing right here. Then I'm going to say, well, this was a block of 2 bytes, and it has just been freed. The problem now is if I call malloc4 again, my program is going to say, well, no, we don't have a 4-size block that I can give you. But you may be saying, wait, why? This block is 6 bytes long, or like 24 bytes long, if I'm assuming that each of these is 4 bytes long. Right, this block is, or well, I'm not doing a good job. For now, let's assume that each of them is 1 byte, 1 byte, and these guys, I think I just have to do a proper example. I don't know what I'm doing, man. Let's see. So I'm also like explaining this stuff, and like you probably know what all of this is. Like if you came to the stream to watch a guy trying to create a memory allocator, you probably know what external fragmentation and internal fragmentation is and all of that. I'm going to be an IA next semester for a operating systems class, and I'm sort of also practicing that aspect. Currently not going great, but I mean that's precisely why I do this. So, but yeah, so let's simply set that aside, and what we have right now is this structure, the size, and the user data. We can suppose that each of these is 4 bytes. So let's do it right now, each 4 bytes. And whenever the user calls something, say, I don't know, malloc2, right? Then okay, allocate 2 bytes for me, or 3 bytes for me, or well, bytes, each of these is 4, so 12 bytes, right? Let's see. OSDev is cool. I attempted a kernel a few times, but all I got out was a bootloader. Damn, dude, that's pretty good actually. Like, see, I feel like many of these projects are often really difficult. Like, it takes sort of dedication and like, committing to them sort of every day, at least like 3 hours of you thinking about it and coding, etc. I've personally encountered myself sort of like procrastinating projects or abandoning them in the middle. So the fact that you built a bootloader, that's pretty incredible. It's very cool and interesting, but takes a long time to get visible results. So yes, exactly. So getting all the visible results it's very difficult. So you just have to to use like your willpower in some sort of sense. It takes a lot of dedication. And something I've also found, at least in my case, is that it's kind of difficult to find the infrastructure to develop it in. What I mean by that is, say you want to create a thread library, right? In my case, I'm sort of starting with all of this, right? Like the experience I have is very few. So getting to figure out, okay, how do I create an actual, like, before even writing the code for the thread library, where do I connect it to? Like, how do I even, interact with the system? Like, what, right? So all of that, it's part of the journey, but I find it very difficult. It's like that pod, but nonetheless, it is really interesting. This whole world of low level, where you look at all the things everybody has taken for granted so far, and you discover a lot of the stuff that powers all of the programs you've created and everything you've been working with. So let's see. You end up running your code in human or some other emulator, and you need to learn to get the same satisfaction from seeing a few bytes. But yeah, well, there's a memory as you normally get from moving a character in the game or getting some data from a socket. I see. Yeah, you seem to have a lot more experience. I didn't know there was like a thing called QEMU. That's pretty good. Like you need to condition yourself to get into. I feel this is the best description of of like lower level programming. Although, as I said, I have not much experience. The few experience I have is basically this. Yeah, before you get a spread driver or something like that ready, theory behind is super interesting. And I imagine that like in your case, this is like even sort of more. It's a lot more. If you were working only with a bootloader, like there's nothing to show on screen. It's not like you can do much by showing super interesting graphics. It's all basically there for the sake of sort of creation of being there. And I agree. The theory behind is really interesting. There are lots of problems that are very interesting to tackle. And yeah, I feel that's a great motivation for systems programming in general, or like low level programming in general. That's why it sort of motivated me to continue. But yeah, Wi-Fi has a baseline graphics driver, so it's much easier. Oh, I see. It used to be with Kazabaz. Okay, but I feel that doesn't subtract much merit from it. Right? It's like I don't know. To me, that kind of sounds insane. Hopefully, I'll get to there. Hopefully, one day in the future, I'm gonna be like, all right, could have bootloader with ZN in the chat advising me. So, we'll see. We'll see. But for now, we have to settle with the memory allocator, which I'm also really excited about. It gives you sort of that same feeling of like, you're just creating something for the sake of it, for the sake of learning, and the theory behind it is really interesting. But yeah, I mean, as I was saying, we are continuing on this sort of. Oh yeah, thank you, thank you for the message, and yes, hopefully I'll be a good idea. But yeah, so here with our memory allocation, right, we have the problem of external fragmentation, but also we get that problem of sort of false fragmentation, where whenever you free something, you maybe the user, as I said, malloc 12, so then you sort of occupy these three spaces, these 12 bytes, and then in your header, which for now it's only 4 bytes long, you include sort of the information. This is 12 bytes long. Then you malloc 4, right? 4, so 4 is going to be like only this guy, and then it's like one of them, right? 1. Maybe you malloc another 12, right? Malloc another 12. And after that, you can say 12, then that's allocated here, right? And suppose that like through allocations, we also get rid of this rest of memory. Now, what could happen is that the user calls sort of free. I'm just gonna call them by their numbers. No, free the 4-byte block. No, this is not the way you would make the call, right? But Actually, let me use sort of their actual index into this thing. So we like 1, 2, 0, 1, 2, 3, and 4 and 5. So that's going to be probably 0x. Well, 20 in hexadecimal is different. So I'm just gonna write 0x20, although it's not the 20th byte, but it is what it is. It's our example. So once you free this, you're gonna get rid of the memory. Now you say, oh, there's a one block that's free, and it's one. Oh, sorry, this shouldn't be a one. This should be a 4. It's 4 bytes long. And then you say free this guy on the side, right? Free this one. So now you say, oh, this is a free block, and it's 12 bytes long. Now, if somebody calls malloc and they ask for 16 bytes, a program is going to say, what are you talking about, right? I have no idea. There are no 16 bytes free. I cannot provide you that. And the reason is because the program sees, or our allocator sees, yes, there is a 4 byte long block that's free, and there's a 12 byte long block that's free, but it doesn't know that they are sort of next to each other and that you could actually combine them, right? So what we must do is sort of have a strategy to look to our left, look to our right. Whenever I free something, is the thing to its right also free? And then merge them. And it's the thing to its right or to its left also free, and then merge those to result in something like this, right? Where I erase this, and then instead of 4, now I have, well, a 20 byte block, and now I can suffice the request. So if the block to your side, so say I'm gonna grab this little thing over here. I'm gonna copy this over to the side, and then the same thing over here, where I'm going to grab this. Perfect, right? So, oh wait, I'm seeing the chat. Let's see. One last thing you might not know, there's a wiki dedicated to OS dev, except it's super old and not really updated since community is scarce, as you might have guessed, but it has plenty of good info and references regarding all this stuff. Oh, what? wiki.osdev.org. Yeah. Watching this, let's see. Oh, wow. It's found a main page. Register machine model of computation. Beginner mistakes. Oh, dude, this is amazing. Thank you so much. How do you know all of this stuff? I feel I should have known this. Damn, this is very cool. I'm gonna add it here to my bookmarked websites so that I can just come back to it. Yeah, thank you. Bare bones tutorial, like hello world. Gotta follow that in the future then. I feel like pretty cool. So I had to use it as my sole resource. Ooh, that's even harder. Damn, dude. Total respect for you. Like, are you still in like university or like graduated already? I'm not sure, but that's incredible. That's incredible. I mean, yeah. Yeah, I feel like that's what makes like a real programmer. Now. The passion for just trying out something that you don't really have access to. But yeah, so okay, that explains what like all this resource. Pretty good. But yeah. Let's see. Okay, so what was I doing before? Oh yeah. So we were you enter more into cybersecurity than programming. Oh, less time and energy for that nowadays. I see. Like, but cybersecurity. I feel like all of this is like extremely helpful for cybersecurity. Although I don't know anything about sort of advanced cybersecurity or anything like it. Right. Most thing I've done an SQL injection in like high school's website, but other than that, nothing else. But I feel like all of this information, all of this sort of OS dev and the low level stuff must be like helpful. I feel like that's a great combination. Used to be super interesting. Pretty good. Yeah. Let me drink water. Bread and butter for cybers. Okay, so that explains a lot. Yeah, I mean, it makes sense. Thank you so much for sort of playing along with me. I'm here sort of talking about memory allocation to an expert, which, but yeah, I mean, I see it's less relevant, but yeah, I mean, memory allocators makes a lot of sense. Maybe like at least from what I've seen, like a lot of the sort of vulnerabilities that are coming out are related precisely to buffer overflows and stuff like this, which is very interesting. You know? Yeah, memory corruption and oh, thanks so much. And yeah, hopefully that answers you guys some stays. I'm not in the age of AI. I've found it a bit sort of unmotivating to code and like do like it seems like people tell you like you gotta push out the code and etc. So I feel there is a value in just doing things on your own and sort of really understanding what you're doing. And but yeah, I mean, it's, yeah. Let's see. I don't want to divert you from memory allocators anymore, but I want to. Oh, thank you, sir. Thank you. No, don't worry. I mean, I appreciate this. I genuinely started this entire stream, sort of having in mind that it wouldn't have any viewers or anyone, or like maybe people would hang around, but they just wouldn't say anything. So I'm very thankful you showed up. This is very, very good. And thank you for the wiki. Thank you for the wiki. Will definitely be a resource I explore, especially in the future. Once I start sort of looking at maybe other things, because today it's a memory allocator. Tomorrow it's going to be something else, right? Like, I don't need that tomorrow because I don't think I'm going to finish the memory allocator today. Especially because it's 4th of July. I'm not American, but I'm living here and I'm currently in America, and I want to see the fireworks and all that stuff that I've never gotten the chance to see. So I don't know. I'll end the stream in like 3 hours, 2 hours, or something like that to go out. But yeah, thank you so much for the resource. But yeah, I mean, continuing here with the memory allocator, one interesting thing is to solve this problem sort of fake external fragmentation. We can simply look to a right, look to a left, and then sort of be done with it, right? And check whether the blocks on our side are free. In this case, if I were to free this block over here, then I would be able to look at the block on my right. Currently, our header only has size in it, so I'm just gonna say size, say and bytes, size. And all I'd be able to do is say, and let's see, size. Perfect. If I free this, then I'll be able to go to the header and say, okay, this is a block of size n. I skip n bytes into the future, and then I advance one more to find myself looking at the size of the next block. And I imagine we would have to have a little sort of flag to determine whether or not it's free, but I'd be able to tell whether or not this block is free, and then I could merge them. The problem comes when we try and look at the block on our left, mainly because now if I try to look at that with the current layout we have, maybe I step back, right? But by how much? Right? If I step back exactly 1 byte, then I'm going to end up in user data. And user data, we don't know what it contains. We cannot trust it. It's going to be completely bogus, useless for us, right? So maybe I want to skip a little bit more, but by how much, right? We don't really know how long this block is. So I cannot travel back to the header to get the information on whether or not this block is free. And also, I wouldn't even know its size, right? So how do I travel back to the header? And that is an interesting question. The more reasonable thing to do is we can simply include a footer over here that's going to store the size information for this block. And that way, I can simply step back once, take a look at the size, and now I know how much I have to skip in order to get to this block's head. So that's how our little sort of blocks start taking shape, where we have sort of now we're accompanied by size on that side, and then size on this side too. Perfect. And that starts to paint a better sort of picture for what a memory should look like when we're working with it in the program. And this would actually suffice for a very simple allocator where we simply hop around, where we're like, once again, this would be sort of a first fit allocator where we don't really keep track, or we have like a contiguous list of blocks that we can simply visit. And we can say, okay, is this guy, is this guy free? Is this guy free? Is this guy free? And so on and so on. And we can go back and forth in the list. This is basically a linked list, right? A linked list where every single node is right next to each other. And the only reason why we needed the size is to deal with frees. So, which is kind of interesting. But we want to do something a little bit more sophisticated. The reason for that is that, of course, like searching for a free block of memory is going to be a pain whenever we have some amount of memory allocated, right? Like many blocks of memory, they're going to be there, and then we're going to have to traverse them all the time. It's going to be painful, and it's going to be like linear search, really bad. So another way to deal with this could be simply keeping a sort of track of not every single block, but only the free ones, right? Making it so that not only do I have, some linear search time, but we need to improve that, right? Like, we cannot stay with a memory allocator, at least if we want to make sort of a serious effort on it, we cannot stay with a linear. And although sort of we're still within the linear realm, we may think of improving this approach a little bit more, where we can have the size, which we always need, but instead of assuming that the next block in our list should be the block that's like right next to it, which, I mean, the problem with that is, what if this block is occupied, right? What if this is not free, and what if this block is also not free? Then I'm going to spend time, right, navigating through blocks that I already knew are occupied, but I'm still including them in my search, and that's very inefficient. So instead of only storing the size, how about we also store sort of this next pointer, in a sense, you could say, right? So here I can have the next sort of information on what the next free node is, and also what the previous free node is, right? So that way, I can, whenever I'm looking at this block, I say, okay, this one didn't really suffice my request. I want to know where the next free block is. And then I'm just going to look at next, and I'm going to skip to wherever next indicates me to go to, right? And same with previous, right? I'm going to be doing that. Although currently we wouldn't need previous, since we are basing things on a first fit, or like previously what we had was first fit, and this is just an improvement on that, so we don't really need previous. But now we have added a little bit more information to our header, and we now have this little guy, this next. And every single block is going to have it too, just so that we can keep track of the design of our little block, right? So over here, this is what we have so far. Now, this is good. I mean, it's like it's still linear search though. Still some OFN. It's a bit less worse OFN, but it's still not what we want. And also, we had already sort of pointed at the fact that maybe first fit is not what we want. Precisely because of this, we're going to have like OFN searching time. So if we are to incline ourselves towards, I mean, as you can see, we already have sort of kind of enough information to suffice with the first fit, first circular fit, and worst fit approaches. They all simply need this sort of contiguous list of blocks or a list of free blocks that simply resembles a linked list. But the best fit approach, that was going to be a little bit, or is going to impose a little bit of a higher challenge. We could have a best fit approach with the information we have right now. How? Well, simply surf through the entire space of blocks and find the one that fits our request best, right? So we already have the elements to perform this fit. The problem, it's going to be linear, and we don't want that. So how do we solve that problem? And that's precisely what I had annotated here yesterday when I was thinking about this problem, before I even thought of streaming. so I have done some sort of thinking off camera, but it's not that serious. So what we have right now is, how do we find the best fit block? And well, we simply look at the data, at sort of our past experience in many coding problems, or maybe in classes or in projects, etc. Personally, the data structures that came to mind when it comes to searching were AVL trees and red and black trees. So the way they work is, well, rather than those two, it's a binary search tree, right? And a binary search tree, I hope if you're looking into memory allocation, I assume you know like about binary search trees. So we could use a binary search tree to look for the block that best fits our request, right? We could say, okay, let's go to the root, right? Does my request require more bytes than this? Yes, well, I'm going to go to the right. Does it require more bytes than this block? Yes, and I'm going to go to the right. No, I'm going to go to the left, and so on, until we reach a point where we find the best fit, by definition of what a binary search tree is. The problem with binary search trees, and especially in the case of memory allocation, where it's kind of unpredictable the amount of data that you're going to have, and not only that, it really depends from program to program, so we need to create a sort of general approach. The problem with that is that binary search trees often create this sort of awful situation where, say you have, I don't know, 1, right? And then you have a block of size 2, and then you have a block of size 3, and then you have a block of size 4, right? Eventually, sometimes, depending on your workload, your binary search tree, it's gonna, rather than a tree, start looking like a stick. And this is, once again, linear search. So can we improve this? And the answer is yes. And for that, we have these sort of data structures called AVL trees and red-black trees. There are other sort of approaches and data structures you can use, but from what I have seen, these two are great, at least for the purposes of this. Now, what is the difference between these two? Well, they perform the same task, which is sort of trying to keep the binary search as complete as possible. That is, sort of compressing its height, the more it becomes like a stick, would be the way I would explain it. AVL trees require multiple information. They require, well, your node's data. They require the sort of left and right pointer. For the sake of deletion, you could require a parent pointer, although that is, we'll think about that sort of in the future a little bit more. I'm not sure about that yet. But you also need the height of that specific node. So you need to store that height. In comparison, red-black trees need your data, the left pointer, the right pointer, and rather than the height, they need only 1 bit to store the color of that node. So I had encountered AVO trees before. I didn't know anything about red-black trees. Because I don't know, I just hadn't seen them. So yesterday I was watching a bunch of tutorials. How does the red-black tree work, etc. And what ends up happening is precisely that. As you see, I listed sort of the amount of information these things need, not sort of or like I did it with the purpose of determining which one to use. Because if you're going to have a memory allocator, you want the memory allocator to be fast, but you also don't want it to implement like some like memory eating beast that just leaves you with nothing. You want your memory allocator to be very sort of thin, right? Use as less memory as possible while still being fast. And in the case of red-black trees, as you see, we get that advantage of the color being only 1 bit compared to the height, which is 4 bytes. Right? Well, it depends on the architecture, of course. I'll assume 4 bytes, right? Well, let's see. The chat. I recently implemented AVO trees for a personal project of mine, and I remember I managed to get by without a parent pointer. Might not be the best optimized version, but they do work without a parent pointer. Okay, yeah, no, that makes a lot of sense. AVO instead of red black because it felt it. Yeah, definitely. Like I was thinking of AVL too, like as an option, but as I said, the memory usage on Red Black Tree is better. That's why I have written like an X here to mark that was my decision and the sort of best mem usage. And yeah, I mean, without a parent pointer, can you get by without a parent pointer? I mean, you say yes. I imagine the way that could be done, it's like whenever, say, you want to, because my only worry is deletion. Right. If I want to delete something from the tree, that seems to me like a little bit of a headache because we're going to have like all of these nodes, right? All of these nodes, right? And when I asked you if these had values, right? Like 1, right? 1, and maybe this one is, sorry, I was about to, 0, and maybe this one is 4, and then this one is 2. Oh my god, these drawings are really bad. Can I decrease the, stroke width? It was really wide. Okay, perfect. 2, and then maybe this one's 5, right? If you ask me, delete from the tree the 5 or like the 4, you could start from the root and then go down until you find the 4 and then delete it. And the way we could keep track of the parent may just be a stack or some sort of variable where we just, as we go down the tree, we keep track of who the parent is. I could believe that. During deletion, I replaced either by entry successor or entry predecessor, but they both were inside of transfer trees. Yes. So in that case, yeah, AVL helps us with that, and that would make sense. My problem is I'm referring to the parent because we need to update this pointer, right? We need to make the one point to like another guy, the new guy that's going to take its place. So we need to keep track of who the parent is. And yeah, I imagine that if we keep track of a variable as we go down, we're going to be able to do that. Let's see. So I only need a reference to parent node to replace a child, which could be done. Yes. Okay. So that makes a lot of sense. My only problem with this, and sort of the thing I'm worried about, because like if we can get by without using a parent pointer, that's gonna be great. Because wait, not sure about red black tree. Okay, I feel like red black trees are like basically the same. Right? Like they're very similar to AVL trees. They also have rotations. They have like all of this paraphernalia that the red black trees also employ. The only difference is that red black trees care about color, and there's some rules included to account for color. You know, everything sort of revolves around that notion of color. But both of them both approaches, independent of whether ABL tree or red black tree, both of them need to keep track of the parent, as you've pointed out, but you can do that with a variable. And my only problem, my only situation with that is if we can get if we can get by without using a parent or storing it here in the memory blocks, that'd be great, right? Because less memory usage, less everything, same speed, awesome. My only problem is that whenever deletions happen in that tree is because somebody calls free. And when they call free, they provide the pointer to the node they want to delete. So rather than giving sort of like, it's like instead of having a sort of identifier, they just say, this guy, delete him, right? So how do I really know like who the parent is and how to update those pointers? And that's the only thing that worries me. And the reason why I think we are going to need a parent to be stored within that block. There is nonetheless the possibility where we could somehow add some sort of ID. Like, I'm not really sure. But that seems a little bit cumbersome, and in the amount of memory you store an ID, the same bytes can be used to store a pointer. So it doesn't really make sense now that I think about it. Let's think. Because, I mean, we do know the size of that node. So if we perform a search, right, if maybe we go sort of down the tree and we use as identifier the size of that block, we could get close to that block, but maybe not that exact block. Yeah, I mean, there could be many 16-byte long blocks that are freed. So you cannot just go and say, okay, delete a 16-byte block, because then it's just going to free some random information that the other person allocated. So maybe not that. So yeah, I think we are going to have to store a parent pointer in our blocks just because of the nature of the problem. But I completely agree that this would have, using the approach you described would have been like way, way better, at least for the sake of memory usage. But the good thing is that now we don't have the cost when it comes to search, right? Like, now that we have a parent pointer, we can immediately know where it is. And so we just simply update the pointers as we need to, and we're all happy, I suppose. So let's see. According to the current plan, what we have is we have the size, we have the left child. After that, we have the right child. So right. And we also need, we'll just use the data. We assume that it's an amount of bytes. We're also going to need to know who the parent is. So here we need a parent. And we also need the color. We're storing a lot of information. Color, but the color is only 1 bit. Oh, shoot. Shoot. I wrote in the incorrect place. Let's see. Color. Then it's just 1 bit. I think I'm gonna have to make this guy bigger to accommodate for all of this. Let me move these guys to the left. Perfect. Let's move them over here, and then the color. Right? Awesome. So it seems like we have given a better shape to what we need. Nonetheless, there is something that, I don't know. Okay, it feels like we're storing a lot of information. The thing is, I don't know what a lot of information means because I haven't coded a memory allocator before. So, I mean, it's sort of based on vibes. I mean, previously we were storing size. So that one, so this is like space we had before. Next, previous, and then that's kind of it. Right? So the things we are adding are parent and color. And color is negligible. Parent, I mean, I can get around having an extra like 8 bytes of memory per block, although it is important that we think about this before even jumping to any sort of implementation. And there's one last thing that bothers me a lot, and it's the fact that the size is being stored twice. Like, it's clear why, right? Because we sort of need it for the sake of the next block discovering where we are positioned. But is this the only way? Is there a way where we can sort of change things around to store less stuff? Because something I'm thinking about is making use of XORs somewhere around here. And what I mean by that is that, I mean, a XOR has a very interesting property where whenever you XOR two things together, well, that's probably often expressed as this, right? Something stored with itself is 0. And we know that XOR is a commutative operation, so it doesn't really matter where, like what happens or like the order in which you perform stuff, right? These two things are the same, and the thing stored with itself is 0. And on top of that, we have associativity, right? We have associativity of operations where whenever you have A XOR B XOR C, that's the same as A XORed with B, and then that XORed with C. It is a very interesting operation because you can encode information using these properties, right? Because if you have, say, A XORed B, and then you XOR that with A again, you're gonna get B back. So there is sort of this kind of interesting thing where if you have the XOR of a thing and you have one of them, you can retrieve the other. So if I want to know what A is, I simply need to XOR this with B, and then this is by the properties going to be the same as this, B XORed with B, and then this is going to be A XORed with 0, and of course anything XORed with 0 is itself. So we get the information back. And I'm trying to think if there is a way we could use that to save memory. Because it seems like an interesting property. I'm not sure if we could exploit it. I'm also a math major, so this is interesting to look at. I don't think I'll spend much time, but let's think about it. And the reason why this comes to mind is because, I mean, there is the usual problem of like swapping variables, right? Whenever you need to have, I don't know, variable A has a value, variable B has a value, and then you need to exchange them. Usually the way this is done in sort of like normal code is, we went to the coding. It's something like, int A equals some sort of value, let's say 13, and then B equals to 25, right? And then whenever you need to exchange their values, what you do is you create a temporary variable, set it to one of them, then set the first one to equal the second one, and then this one to equal that, and then they have exchange values at the end, right? But we can use the properties of XOR to make this even faster. And the way to do this is rather, I mean, you simply sort of would need to XOR A with B, right? B hasn't changed its value, but now you can simply sort of sorry, I'm getting all confused. A XORed with B. That's what we have on that front. And now, oh yeah. B would be equal to A XORed with B again. So now it's equal to A, and then A is equal to whatever it was storing before stored with B. Yeah, there you go. So I think it's something like this, right? Where you make A store the value of A is now equal to A XORed with B. Then after that, you have that B is equal to whatever A has. So it would be A XORed B. And then you XOR that with B. So now these two cancel, and now you end up with A. And then here, to retrieve the value, you use that property, right? And then A would just be equal to A, which is currently storing XOR B, XORed with whatever B is currently storing, which is A. Like it's okay. I named the variables like the same as the values, but I hope it's understandable. And then you end up exchanging the variables without needing to create a new temporary variable to store them. So something like that, something that we could use, maybe like combine these two guys together and like store them with something, and then we end up having like all that information condensed into one single spot. So let's see, because let's see, if we are traversing the tree, right? This is the information that we have. As we traverse down the tree, we know what the parent is. So that means maybe we could store something like the parent stored with the left child instead of left and parent together. Yes, it is a possible optimization. It doesn't change. Yes. The underlying logic is the same. This is mainly for memory concerns, right? That like we because an extra parent, like this extra parent guy, represents 25% more memory usage, like compared to a previous approach. So although it's only 8 bytes, it is like, you know, like 25% of memory usage increased just by the existence of this guy. You know, it's like it feels a little bit wrong. But I agree, it doesn't modify the logic at all. Because what I'm thinking about is like, as we traverse down the tree, we already know what the parent is. So maybe we can just store the XOR between the parent and the left. And then simply to get the left, we XOR it with the parent, which we already know. But that would be useful while traversing down, which we already said doesn't even need a parent. So for the sake of deletion, would this piece of information be useful? And my guess is, well, no, right? Because if we only have this piece of information and we do not have left and we do not have parent, then there's no way we can retrieve either of them back. Because you need one to retrieve the other one, and that's just not something we have. So, well, I guess this, I'm gonna like start saying crazy terms, but I guess this goes, yeah, no, actually, this is mathematically impossible. Like, I don't even know what I'm talking about. Like, information theory already tells me like the sort of smallest amount of information or bits that you can use to represent something, and we are sort of coerced into this position where there's no way we can compress information without losing something, right? Like, and in this case, all of these variables are we cannot sort of get rid of them. So I guess the XOR doesn't violate any sort of information theory, because precisely one of the requirements is you need one of these two things to retrieve the other one. So if I already have left, I could retrieve parent, but this XOR is occupying the same space that parent would have occupied in the first place. So I'm not sort of doing anything like XORing two things together. Like, the amount of space that you need to employ in order to perform this technique is the same as if you had the two separate values. And yeah, so it seems like it's a rather pointless optimization, because you would always, yeah, we would be violating information theory. Like, so I guess never mind. It was a good idea to entertain. So let's simply go with let's see. Unless you had info about parent. Yes, exactly. If you had info about the parent from before, I agree, right? Because you would still have sort of two pieces of information, right? Like you just have the parent as an extra thing that you were carrying down, and you can use it to unlock what the XOR was storing. But yeah, with random access, it just simply seems like it's not going to be. So yeah, I mean, I guess this is our design, and I totally agree. It would be a bit of a fruitless pursuit. One last thing we need to consider is that color is only 1 bit long, and we, of course, I mean, we could perform some sort of bit packing to simply say, like, all right, store color in 1 bit, but hopefully, well, we need to consider the fact that we need alignment. I mean, we need memory alignment. Although, right, processors these days like don't really require memory alignment like as much. Like, the performance penalty that you obtain from not having your memory aligned is very small with new processors, but it is definitely good. Like, it's something that it helps, and it's good to keep in mind. And yeah, alignment probably helps. Yes, exactly. So alignment probably helps. And my problem is that there's one color bit. like, this guy's just going to misalign absolutely everything the user has after. So we either need 1 byte for this guy, or I'm thinking right now we could sacrifice. We could have a little bit of a trade-off where our size is always like our size. Let me think. Our size is 1 off all the time. So it's like the size could have 1 more byte than it actually does. And what I mean by that, it's like, you have like size, and in right, and in these bits that represent the size, maybe in this last one we can just simply say, okay, this last one is going to be the color, right? Problem is we lose expressive value, where the amount of information that we can sort here, or like the max size of a block, stops being sort of these 2 to the 32 and becomes 2 to the 31. And I don't think that's something we want for, like, as per the spec. We cannot do this. But we could also simply say, no, I mean, this is the color bit, and we interpret the size to be this entire thing. So if the color bit is 0, the size is going to be like, I don't know, suppose the size was like 4, something like that, right? So it would be 1, 2, 4. Oh, sorry, 4. Wait, 1, 2, 3. Can have an extra one. Yeah. So suppose the size is 4, and what we're doing now is we are considering using the least significant bit as color, in which case, if the color is red, then this would be a 1. So size would be 5 instead of 4. And I mean, I feel this is decent enough, right? Because the only thing, we can only miss the size by 1 byte. So we always allocate just 1 byte more than we would actually need, and then just store it here. But I guess it defeats the entire purpose, right? Because if we are to allocate 1 byte more by taking into account that this could be a 1 when it actually doesn't need to be 1, that 1 byte more that we allocate, just trying to be cautious, is the 1 byte we could have used for the color. So never mind. Let's see. With no counts to parent node, yeah, alignment can actually help you because left, right, and parent will probably be aligned to 4 bytes, so you have 3 bits free to store extra data. Because you know that when actually retrieving the left, right parent values, you will ignore them, or size 2 for that matter. 2 bits actually. Okay. Wait, let me read this. Alignment can actually help you because left, right, and parent will probably be aligned to 4 bytes. I agree. Yes, as per the spec, I think I think the max size of the heap we're allowed to have is 2 to 32. So okay, yes, I agree, 4 bytes. So you have 3 bits free to store extra data. Okay, what do you mean by that? Oh, 2 bits actually. Okay. Because you know that when actually retrieving the left, right parent values, you will ignore them. Or size 2 for that matter. 2 bits actually. Wait, could you explain what do you mean? Where are we getting these 2 bits from? Because the blocks will hopefully start aligned. So try to think what you mean by this. If they're aligned by 4 bytes, this would just be 4. This is 4, 4, 4, 4. All of them are 4. User data starts aligned at a 4 byte sort of consistent address. I'm not seeing where the 2 bits are coming from. Well, because access to 4 aligned pointers on x86 is faster with some instructions, and no matter what user allocates, you might want to pattern until length that's aligned to 4 bytes. Pointers will always end up with the lowest 2 bits clear. Oh, okay. Okay. I kind of see what you're saying. I didn't know that x86 is supposed to... Yeah, no, I agree. 1, 2, or 3. I see what you're saying. Damn, I feel it's a bit of a convincing argument. Although, because like we're going to try to align the, I mean, from what I'm seeing right now, right, the entire block is hopefully 4 byte aligned. So this will start at a 4 byte aligned address, which means that this will also be 4 bytes. So it's perfectly aligned, nothing left to, they're not sort of wasted bits, if I want to say that way. Then same for this one, same for this one, same for this one, because rather than pointers per se, which would be like the 8 bytes long or whatever, we're gonna store like 4 byte versions of them since the heap is only 2 to 34. And then once we get to this point, everything was like perfectly aligned. So there was no need for sort of wasting or like, because maybe here at the beginning, right? Yeah, exactly. Offsets with a base of 0x0. Maybe here there could be some extra space that was needed in order to perform the alignment of this block to be a 4 byte sort of 4-byte aligned block. And so if I'm interpreting you correctly, you're suggesting to store the caller here. But I think it's what you're saying. If not, let me know. My only thing is that, oh, no, not at all. Okay, wait. I'm misunderstanding. Let's see. Wait, I want to understand what you're saying, because this is something. Let's see. I'm going to read your messages again until I understand what you're saying, because I want to take this seriously. Let's see. Alignment can actually help you. Yes. Left, right, and parent will probably be aligned to 4 bytes. I agree. And you have 3 bits free to source data, because you know that when actually you're retrieving the left, right parent, you will ignore them, or size 2 for the matter. So I understand that we agree they're 4-byte aligned. If you need them to be 4-byte aligned, then you will have like 1, 2, 3, 4, 5, 6, 7, 8. These 2 bits at the end will sort of always be 0 for the starting address of one of these guys, right? Because it always needs to start at 4, so the starting address of this will always sort of have these guys set to 0. Right? Same for this, same for this, same for this, right? So yes, I agree with the starting address being 0 and. Oh wait, no, I'm kind of starting to see what you're saying, because yeah, okay, no. I feel like I understand now. Let me read your messages before I say something stupid. Not actually sure if it will work, but I think it will. If you have a pointer that ends in binary, yes, it doesn't matter, because you know all of the pointers need to be 4 aligned to the bottom of it. Yes. The volleyball just click. Yes. Yes. Okay, this makes a lot of sense. Okay, yeah. No, that's an awesome idea. Okay, no, I see what you're saying. So left will always have to point to another block. And we say that blocks are 4-byte aligned, which means that no matter what happens, these 2 bits at the end of that block's address is something we simply just don't really care about. Yeah, I mean, this convinces me, to be honest. Yeah, no, that sounds great. Dude, this is amazing. Let's see, is there anything we may be missing? Like, I don't think so. Yeah, no, I feel this is a great idea. We can simply store the caller in the 2 bits that parent doesn't use. Well, ZM, you that was a great observation. So I'm just gonna write that down over here, because it's a great contribution. Let's see. As per ZM's recommendation, so or like idea, we can still caller in last 2 bits. Last 2 bits of parent. Blocks are aligned to 4-byte address. So last 2 bits can be ignored. Perfect. Yeah, no, this sounds great. So let's keep it here. Let's see. He's like, in fact, I'm pretty sure malloc API in Linux, whatever, is not guaranteed to allocate the precise number of bytes that you request. Yes, I agree. I was reading the man page for malloc, and yeah, it allocates at least 10 bytes, but it might allocate more. Because of the alignment speedup on x86 CPUs, malloc usually allows woes and yeah, okay. As in, it passes the lines to 4 anyways, yes. And then you do yes. This makes sense. This makes perfect sense. And yeah, great idea. Like, pretty good. This. So now we are going to have. Let's sort of restructure things a little bit so that we can have these two guys coexisting with each other. Parent and caller. I'm going to have them. I'm going to separate them with this like little dotted line, so that like they're still together, but we think of them as separate, but they're sort of in the same amount of bytes. They're coexisting. Okay, no, okay, that solves the alignment problem with caller, because caller would have offset everything by like 1 byte, and then everything would be like completely screwed over by like to the right. Uh, Great. Okay. Yeah, no, completely agree. Yay. So it seems like we have reached a final design. The use of like full bytes more of memory annoys me a little bit, but it's okay. I think we can live with that. And as per the user data, the size, yeah, those all stay the same. These two, like size having to be duplicated in the same block, also is a little bit annoying, but we already discovered that this is sort of needed. And yeah, if I mean this sounds pretty much, yeah, pretty good. See, I'm not sure if you need all left right parent fields, because I'm not that good at the data structure side of things, but I'm sure you can squeeze the 1-bit color into either an offset or size type of field in the bottom 2 bits. Offset or size type of field. So what do you mean? So currently I'm storing the color in parent, but I agree that this like color could be stored in the lower 2 bits of either right, left, or size. Doesn't matter which one. We could go crazy and as in left, right, apparent, left, right, and parent are offsets, and size is size. So I'm not sure how many of those fields you'll finally need, but at least one of them. To store color, I agree. Either to store color bit. Yes. Okay. I agree. Because okay, like even though there are offsets, they're still gonna need the full 4 bytes because like our heap isn't. I don't remember. Oh well. I think they're still gonna need the full 4 bytes. So okay. I agree we could store the color bit in either of them. I'm not sure if I like understood well what you were like where you were trying to steer me towards or steer me to. But yeah, also there's like 5 people watching. This is incredible. All good. Oh, okay. So I'll take that as in like I mentioned what you tried to say, or maybe you changed the idea. But yeah, if I ever misinterpret something, please let me know, because I mean, there's also like like you guys are here watching me. I want to respect like the ideas and to really understand it. Like it also helps my understanding, right? Like look at the right. I wasn't really getting the alignment part that you or like what you were trying to refer to, but after a little bit of iteration, yeah, we got to like a wonderful solution. So that's great. And yeah, I think this is our final design, I would say. I'm not sure if anyone disagrees with it. Like, speak now, or what is the thing that they say at weddings? I don't know how to say it in English. It's like yeah, whatever. Like, yeah. So yeah, I guess this is our final design. Great. Now we must proceed to the actual implementation. So one thing I do have to mention is that we may be encountering a situation here. As I said before, I only knew of AVL trees in the past because they're the sort of the ones I've used before for projects and stuff, and the ones I've learned of. I didn't know about red black trees. When thinking about this problem, I was like, okay, I know AVL trees exist, but let me see if red black trees offer a better sort of alternative. They happened to offer a better alternative. The problem is I don't have experience with them, and I know the concept of a red black tree and like all of these rotations and stuff. Never implemented one, and we will need to implement a red black tree. So one of the things I'm thinking of doing is before even jumping to the memory allocator, I need to implement a red black tree, and then basically just sort of copy the behavior that we have in an implementation of a red black tree. And instead of nodes that you allocate on the heap, you're just going to use sort of this sort of funky block thing that we have prepared. But I definitely find it necessary to write an implementation of a red black tree. So yeah, I think that's what we need to do. I had thought about that yesterday, although yesterday my design didn't look like this. It looked like everything like that except for ZM's idea, which is awesome. So yeah, so I have created what was the name of it? I think it was like let me okay, I have Chrome on my side. It's like created a think, let's see, file. I'm pretty sure it was called data structures. Yeah. So I created this little guy where I'm just going to start storing implementations of data structures. So from scratch implementation of data structures is a very simple thing. And I mean, all I have is a git repo. Reset. Let's see what that does. Reset. And I'm just gonna trash this out and show it again. Great. So yeah, I'm feeling I'm not ready to start with the memory allocator like immediately. I'm going to build the founding blocks. So first start with a red black tree data structure and implement it from scratch. This is gonna be boring, right? Because it doesn't really correspond to the title, which is coding a memory allocator for. Well, I guess it does, right? Like we're building the memory allocator. We're just building the data structure that we're going to use, and that's gonna be a red black tree. So yeah, I mean, from now on, I think I'm gonna be working on creating the red black tree for around what, like 1 more hour. I'm here in PST time, so it's 5 p.m. currently. So at 6 p.m. I think I'm gonna stop to go out and look at fireworks and stuff. As I mentioned before, because it's Independence Day, and I mean, once again, not American, but it seems like a pretty beautiful holiday. So yeah, but I think I'm gonna dedicate my time to creating sort of like a red black tree data structure. Let's just call it RB tree. Let me see. So we would need rtree.h, of course. I imagine this is going to be templated. So I'm not going to create a CPP file. I think this is sort of what we would need for a red black tree. Yeah. Okay. I mean, also, sorry, but you're going to notice that I look down a lot. The main reason for that is that I have been coding since I'm very young and all of that, and I've been really passionate about programming, but I never really learned how to type correctly. So I kind of just like move my hands intuitively, and I still need to sometimes look at the keyboard. Although I type fast, I'm trying to get rid of that habit. I'm trying to learn how to type properly with like the hand positions and all that stuff. So sometimes you're gonna get really annoyed at me where I'm trying to type something, and then instead of typing the thing I wanted, I press like a key that is like right beside it, and then I'm like delete that, and then press the wrong key and delete that. That's because I'm getting used to not looking at the keyboard. So uh, bear with me. Okay. So what are we going to need to include for now? I think, oh, nothing really, right? So, okay, template. I think we're gonna need. Oh, sorry. You know how that has to say. We're gonna need a template, and we're gonna need a type name. So there's hopefully a red black tree that can support any sort of data that you want to store into it. So you're gonna need that data, but we're also gonna need to ask for a comparator because they could pass some sort of data that we don't know how to compare. An example, the blocks in a memory allocator. So we need a comparator. And let's create a class, let's call it arbitrary. An arbitrary for red black tree, of course. And okay, so what are the things that our red black tree will need? So these are going to be our sort of like our attributes, attributes, and then I'm just going to write this down like that. And then here we're going to have sort of methods. All right. I'm just going to label them like this so that it's clear while we're developing. For our attributes, we're going to need the data that we're going to store in that node. We're also going to need a pointer to the sort of left child. We're going to need a pointer to the right. Oh, well, it wouldn't be it would be another arbitrary pointer. And then an arbitrary pointer to the right child. And in this red black tree, we also, I mean, as we mentioned before, we're going to use a parent, right? And is there anything else we need? So what should a node have? A node should have, I'm going to create like a little arbitrary.xcali draw so that we can talk about it while we're, a node should have, oh, color. Completely forgot about the color. Yeah, you're totally right. So we could either decide to make it an enum or a char. I'm going to make it an enum. Color, and then ask it to bit pack it into one. I'm currently not too worried about memory alignment right now. This is just like a general data structure implementation. We are going to use this in our memory allocator, but it will have to have some modifications. But I just want to create the data structure first so that we have it. And I guess that we can simply create an enum class for call. Where is the L? Color. There you go. For color. And we could have simply red and black as the two members of the class of the enum. So here we have color, data, left, right parent, and I guess we also need sort of a comparator here, an instance of the comparator that we're going to store. And that seems reasonable until this point. So what are some of the methods that we're going to need? Well, we're going to need a way to insert something into our red black tree, and that's going to have is going to be a variable of type t, parameter of type t. We're also going to need to insert something. We're going to need to delete something from the tree. Well, delete is a keyword, sorry, remove something from the tree. How are we going to know what to remove? Well, I suppose that because of the use case with our memory allocator, we could consider just having remove be something that doesn't have parameters. Let's see. I guess mem allocator version won't be templated by t, right? Since it will just be bytes all the way down. Yes, it technically, yeah, the t will just be like whatever structure we have, because once we put it in the memory allocator, we already will know what the what the data type of whatever we want to store is. It will be bytes, but it will be keyed by the size of the bytes. Yes, exactly. The little t is just gonna be like some sort of the whole block structure, but comp will only compare the sizes as keys as it goes down the tree. So yes. We are here inserting, so okay, to insert something, and I'm just trying to sort of create the general data structure. And then now that we have an understanding of how it works and like all of the perks, we can simply copy the code and adapt it to a memory allocator once we really understand how to do it and once the difficult stuff about random black trees is solved. Because right now we have insertion, right? And then removal, right? Removal, well, there are no such thing as like unique things, so there's not like an identifier of what to remove. We could simply just have it be a member of a node, like just have no parameters, so that I can just call like node.remove, and then it just removes it from the random black tree. That would definitely fit our use case for the memory allocator, where we only have the block and we don't really have like anything else. But yeah, what if it removes a node at a given pointer? I like, like you mean, yes, like for the memory allocator, right? The red black tree will look a little bit different, right? Remove will probably accept some sort of like pointer to whatever we need to remove. But I'm thinking about this in the more like general perspective, right? Like, what if we had a red black tree that has like integers, right? I feel that's a better way, because I want to think of like the red black tree first and understand like how it works and how to code it. So I think for now I'm going to assume that the t is sort of like an int. And in the case of an int, we cannot really specify like whether or not to, like how to specifically identify that int. The user could just pass a pointer to the thing they want to remove, which is correct. It's exactly what you're saying. But whenever they have a pointer, it means that they also have the object itself. So maybe they could just provide us the node, but if they have the node already, they can just call remove on that node. So I think I'm gonna leave it like that, although I think it's really subject to change. Like, I'm not sure about the remove. Let's focus on insertion and all that stuff for now. So insert, remove, and we also need the most important of them all, which would be like search or like find. And find, of course, would need to return something that is of the type that people want. Okay, let me think about this. So we want to find the value that's closest to whatever you like the user provides, and then we want to return to them the node that has that. So we're gonna just return a pointer to the node that contains that information. Yeah, I think these are like the sort of three basic operations. So insert, find, and then remove. I feel I'm not sure if I'm missing something, but it seems like this is fine. Maybe. Yeah, I mean, anyways, we're still gonna need a constructor. But for now, let's just keep it like this, and we'll create stuff whenever we need it. So we have the red black tree. Those are its methods, its attributes. I think that's sort of its general shape. So great. All right. So we have to pull up a little like, let's see. Let me think of how to do this, because I need to read a guide on maybe on red black trees. So I'm not sure, like I haven't memorized exactly how they work, although I have a general idea. And So let me find a way in which I can just stream the not only the Visual Studio code, but also my browser. Because I mean, I could share the entire screen, but I'm not sure if like what if somebody like calls me on WhatsApp or something and then I leak their number. It would I would have to apologize to that person. Um, you have just added a browser source. Oh, what? Okay. Um, well, let's see. Let me remove that guy, and maybe I can add a different window. So we're on the browser. I can add a window capture. So macOS screen capture, create new, and then I can window capture my browser window. So something like, ooh, oh, what's going on? What's going on? Here we. Sorry, guys. I'm completely new to this thing and I don't know how to use it very well. Perfect. Yes, I have. Okay, currently on my screen, I'm seeing like a split version of this. And then I can just. Let's see. Mark on screen share. Device screen. Let's see if I remove. Okay, great. Now I can add a new source for the screen capture and make it be window capture, and then it should capture my Firefox tab. Yay! Awesome. Okay. Yeah, this is great. All right, so, oh no. Wait. All right, I'm gonna have the Visual Studio code on that side, and then this guy on this side, right? If people can see it. And then I'm just gonna make them occupy sort of exactly half of the screen, question mark? Yeah, something like that. And I'm just gonna hide the... Dude, why is this so difficult? Let me see. Yeah! Awesome! Yo! Perfect! We did it. We did it. Okay. We are successful. Great! Awesome. Okay, I think that works. Well, actually a little bit more to the... Perfect! Perfect! Yo, did it. Great. Awesome. Okay. Let's see. Let's see. Let's see. I'm gonna you. It's kind of late over there, so I'll be heading to sleep, I think. I don't know if time difference will allow me to catch a future stream, but hopefully yes. All I know. Dude, ZM, thank you so much. A great viewer. Honestly, as I said, was expecting to start the stream to have like nobody around, and you suddenly showed up, so that's great. And yeah, no, man, good luck with everything. And to the rest of the people that are here, you guys are just gonna watch me code and everything. So have a good night, ZM. And yeah, look, I'm not sure where I'm gonna be streaming, when I'm gonna be streaming. Mainly because I am on an internship, so during the week I work, and probably when I get back home, we'll see. I think Twitch notifies people if I stream when they follow or something like that. Which, by the way, thank you for following. I mean, my first follower. That's kind of insane. So yeah, I'll see you, ZM. Everybody, please say goodnight to ZM, and we'll see how far we can go. All right, see you. Good night. Bye bye. And all right, we will continue here working on our implementation of an AVL tree. Sorry, red, black tree, red, black tree, red, black tree, red, black tree, and we can work with, I guess we can just read the page for Geeks for Gigs, but geeksforgeeks.org, and let's see. All right, so implementing a red and black tree for our memory allocator is going to be a little bit of a boring part, I would say. You may be asking yourself, viewer, why are we implementing a red black tree when the source code is everywhere online? And the reason is I just want to do this from scratch. Once again, everything for the sake of learning, for understanding, and yeah, because I mean, you know, there's not that many red and black trees out there, so we just gotta get a new one. Let's see. Insertion. So inserting a new node involves a two-step process. BST insertion followed by fixing red-black property violations. Consider that if the parent of the new node is black, no property is violated, and if the parent is red, the tree might violate the red property requiring fixes. After inserting the new node, okay, so I feel this is better explained. Like there has to be some video. Oh no, actually no, there is a video. I remember watching yesterday the what's his name? Michael Blossom? Michael Blossom. I don't remember exactly. But let me look it up. The red black tree. Let me. Ooh, my PC is slowing down to dimensions you cannot even imagine. I am not sure why. Let me close some of these things so that I can just have what was I gonna look for? Wait, before that, what are the results of the work of matches today? Sorry about that. Sorry for deviating a little, but I'm just curious. Oh no, France with Paraguay. Man, that's crazy. Okay. All right. Now for what we came for, red black tree, YouTube probably. We'll find some sort of video. Michael Sample, there you go. So he definitely explains red black trees. I'm going to skim over this a little. Try and actually, do we have? Actually, no. I think I'm gonna stick to the guide. Although Geeks for Geeks is the thing that's killing my RAM. Red black tree. Let's find the Wikipedia page maybe. Oh, this is great. All right, Rudolf Bayer. I think red black trees came after the evil trees. Let me see. Implement. Oh no, I don't want to see that. I don't want to see that. I just want to know. Wikipedia is not very helpful in this case. Maybe program is. Oh, there you go. A red black tree satisfies the following properties. Every node is colored, either red or black. The root is black. Every leaf, including the nils, are black. Sorry, every nil leaf is black. If a red node has children, then the children are always black. And the depth property, which is that for each node, any simple path from this node to any of its descendant leaf has the same black depth number of black nodes. Okay. Perfect. Each node has the following attributes. It has caller, key, left child, right child, and parent. And I feel that's exactly what we have included here. Left, right, parent, caller, data. Yes. Perfect. All right. How the red black tree maintains the property of self-balancing. Oh, we already sort of know this. Operations on a red black tree. Various operations can be performed on a red black tree are rotating the subtrees in a red black tree. So there's a left rotate. So in a left rotation, the arrangement of the nodes and the right is transformed into rearrangement. Okay, let's see. If the initial tree is this, if y has the left subtree, as on x as the parent of the left subtree of y. Okay. Okay, I see. So we want to come from this and end up with something like this. Awesome. So we're sort of like rotating the nodes like left this way, right? So I think in the Excalibur, can better see this as like, you know, there's this node and this node, and then this node, and then this node, where now if I label them like 1, oh my god, that's awful. 1, 2, 3, and 4. Oh, like this doesn't respect any sort of like red light tree rules, but to rotate, we simply need to move these 3 guys sort of like to the left. So now 2 is the root, 1 is the child, right, on this side, and then what? Why? Because the parent. Okay, I see. 1 and then 4 would be here, so we rotated them left, and the 3 is inherited by 1. Okay, yeah, this sort of makes sense. We're just rotating it left. Okay, let's just write the code for that. So we have our red black tree. Let me see if you guys can. Man, I'll have to fix my my setup for next stream, because currently I just have like see, I wish I could just share my entire screen. I'm just scared that like somebody will call me on WhatsApp or something and their number is gonna pop up and then I'm gonna be ruined. Or that I leak some sort of information that's important. But yeah. So I think I'm just gonna keep it. Oh wait, I think in OBS you can have something called scenes. So I can just call this one browser. I can have like a, ooh, yeah, we went dark. Sorry about that. Let me now add a source, right? I can have a screen capture source. And then that source can be this guy, which would be the browser. Yeah, and so now I can simply transfer this to the place it belongs to. Yeah, so now it's full. And then I can just, let's see, Control F. What is it? Okay. So did that change anything? Wait, I'm not sure what happened. I think I may have I may have screwed up. Oh no. That's okay. Hello. Hello. Yeah, I think I screwed up big time. I moved everything because I wanted to improve it, and now we are in the dark. Hello. Wait, I think I come back to life. Did it come back to life? Hello? Oh yeah, wait, it seems like it. Yay! Hello people. Um, so I'm gonna remove this guy, and I'm gonna make this guy fit the window. Yeah, there you go. So now we have full Visual Studio code there, and then we have these two guys, so you can switch between them. Perfect. Yo, awesome. So my thing is like, why? Mm, yeah, I'm not seeing myself on the other side. So how? Okay, what happened? I'm going to stop streaming and then stream again, and we'll see what happens.